Hello and welcome to another Common Core Algebra 2 video by eMathInstruction. My name is Kirk Weiler, and today we're going to be doing Unit 10, Lesson 11.5, the sum and difference of perfect cubes. Now this is an add-on lesson because what we've been seeing on the New York State's Regents, at least, is that on occasion they have factoring using both the sum and the difference of perfect cubes. So we added that to our curriculum, all right? And today's video is going to explore that topic. So let's get right into it. Now, one thing that you've studied this year already are what are known as polynomial identities. And these are a little bit tricky for students because what an identity is an equation that's true regardless of the values of the variables. So, you have your equations that you solve, and maybe they're valid for these values or these values. But polynomial identities, for instance, like 10x plus 15, y is equal to 5 times 2x plus 3y, that particular equation is true no matter what value of x and y you plug into it. This side and this side would be the same, so it's known as an identity. Likewise, this is also an identity. X squared plus 6x minus 4 equals x plus 3 squared minus 13. Grab any value of x, plug it in this side, plug it in that side, they're going to give you the same value out. Therefore, it's known as an identity. Now, one of the most famous identities is called the difference of perfect squares. When we have something that has this form, x squared minus y squared, it can be rewritten equivalently as x plus y times x minus y. And you use this in a variety of different ways to simplify things, rewrite things, right? We recognize that structure. We can rewrite x squared minus 25 as x plus 5, x minus 5. 4x squared minus 81 is 2x plus 9, 2x minus 9. And note, the key with identities is the idea that we can take these three things and we can replace them with these three because they're equivalent, right? Identities work no matter what, all right? They're always true. What we're going to be doing today is we're going to be looking at the sum of perfect cubes and the difference of perfect cubes. Now, just like the sum and the difference of perfect squares, the sum and the difference of perfect cubes also have formulas that go with them, all right? They are much, much more complicated than the difference of perfect squares, all right? I mean, x cubed plus y cubed equals x plus y times x squared minus xy plus y squared, and likewise for the difference of perfect cubes. A lot of teachers will recommend, maybe even require, that you memorize these. And there's a real argument, especially from the perspective of just being able to do well on a test or be able to solve a problem quickly in actually memorizing these. But what we're going to take a look at in the development are ways that you can kind of avoid memorizing these patterns while still being able to produce them if needed. So let's get right into that in exercise number 1. All right, let's take a look. Exercise 1. Consider the polynomial function f of x equals x cubed minus 8, which is shown graphed below. All right, so we've got this great graph, f of x equals x cubed minus 8. Now letter A asks, how has the graph of y equals x cubed been transformed to produce the graph of f of x? This is just a transformation question, so take a moment now and answer the question. All right, well, it's simple enough. By looking at the formula for f of x, right, compared to y equals x cubed, subtracting 8 from f of x, or sorry, from the x cubed, simply shifts y equals x cubed down 8 units. That's it, right? When we subtract or add to an overall function, we're vertically shifting it in the direction of that addition or subtraction. Subtract, we shift down, add, we shift up. And then that produces, right, a graph. Here's y equals x cubed in the blue, y equals x cubed minus 8 in the black. All we've done is taken that blue graph and shifted it down 8 units. All right. Letter B says, what appears to be the only zero of f of x? What must be a factor of x cubed minus 8 based on this zero? So I'd like you to think about that. Again, don't look at y equals x cubed. Just look at the graph of, in black here, what appears to be the only zero of f of x? Well, zeros are just another name for x-intercepts. And right here is the only x-intercept of that graph. And it appears to be at x equals 2. Now, we don't have to just base this on the graph. We can actually show that x equals 2 is a 0. Because besides being the x-intercepts of the graphs, zeros are exactly what they sound like they are. They are values of x, typically, that when substituted into an expression, give us 0. And in fact, there's no question that 2 cubed minus 8, which is 8 minus 8, is equal to 0. Now, what factor, this is maybe the more important part of the problem, what factor of x cubed minus 8 must be there if x equals 2 is a 0? What factor corresponds to that 0? And that's, right, a factor of x minus 2. Think about the zero product law, right? If x equals 2 is a factor, if x equals 2 is a 0, x minus 2 is a factor. And if x minus 2 is a factor, x equals 2 is a 0. There's a one-to-one correspondence between zeros and factors. Okay? Now, let's take a look at using polynomial long division. Okay, letter C says, use polynomial long division to write f of x as the product of the factor from b and a quadratic polynomial. So in other words, f of x, right, is x cubed minus 8. And we know that x minus 2 is a factor of it. The question is, what should go in there? And it's got to be a quadratic. It's got to be something with an x squared in it, because this is an x to the first. We've got to have an x squared in here to get an x cubed there. Well, in order to figure out what that factor is, we need to divide this by this. And we're going to do it using polynomial long division. Now remember, that would kind of look like this. All right? But doing this is just a little bit dangerous. Okay, not because I'm so far over on the side of the screen I might just accidentally get out of it, but it's because I'm lacking an x squared term and an x to the first term here. So what I'm going to do is I'm going to actually erase this and give myself just a little bit more room. Scroll, scroll, scroll. And I'm going to write it like this. X minus 2 into x cubed plus 0x squared plus 0x minus 8. All right, so now let's do a little bit of polynomial long division. You'll get plenty of chances to do it on your own during this video, but let me remind you how it's done. We want to put something up here that makes sure that when we subtract, we can get rid of the x cubed. And whatever's up here is going to have to multiply x minus 2. So what we're going to write up here is x squared. And then just like normal long division, which it's probably been a while since you've done, we're going to take that x squared and we're going to multiply it by x minus 2. And we're going to write down the result here. That's going to be x cubed minus 2x squared. Now, I want to subtract this from this, but I have to watch out. Doing x cubed minus x cubed, whatever, that's simple. Nobody's going to make a mistake there. The whole point there is that they get knocked out. They go to 0. But now I have to do 0x squared minus negative 2x squared. And of course, a lot of people get that wrong because they do 0 minus negative 2 and they get negative 2. That's not the case. The easiest thing to do in polynomial long division, because you've got to subtract this from this, is simply change the sign of both of them, and then instead of subtracting, we add. X cubed plus negative x cubed is 0, and then 0x squared plus 2x squared is 2x squared. And then just like in normal long division, we're going to drop that next term down, which is just 0x. Now, up here, we want to write something down that's going to be able to get rid of our 2x squared. For that, we're just going to have plus 2x. Think about that. If I do 2x times x, I'll get 2x squared. So I'll do 2x times x, get 2x squared. Do 2x times negative 2, get negative 4x. Again, if you have no problem subtracting this, great. If not, if it gets a little confusing, change both the signs and simply add. When I do that, those two will knock out, and I'll simply have 4x again. Drop down my negative 8. All right, 4x minus 8, What do I have to do? Multiply this by? It's got to be positive 4. So if I do that, 4 times x is 4x. 4 times negative 2 is negative 8. And then when I do that subtraction, I have a remainder of 0. Now, just as a reminder, that remainder of 0 tells me in no uncertain terms that I was right. X minus 2 is a factor of x cubed minus 8. All right? But now I know what the quadratic is. I know what should go up in the question mark. It's this, right? So now I can say that f of x is equal to x minus 2, that almost looks like a 2, times x squared plus 2x plus 4. All right? Nice. Now, typically, when we factor, we can maybe factor this, but then we have to look at how we factor that. Let's take a look in letter D. Letter D says, calculate the discriminant of the quadratic from C. All right, so let me just rewrite our answer down from C. From C, we saw that f of x was equal to x minus 2, with a little dot under the x, go away dot, times x squared plus 2x plus 4. All right? Now this question says, calculate the discriminant of the quadratic from C. Why does this show that the quadratic cannot be factored additionally? So most of the time we would want to take that quadratic and break it down into the product of two more linear terms, okay? But let's take a look at the discriminant. Remember, the discriminant is b squared minus 4ac. And if we calculate that for this quadratic, what we see is our b is 2. So we get 2 squared minus 4 times a times c. So that's going to be 4 minus 16, which is negative 12. Now think about what that tells us. All right, we did a little bit of work with the discriminant earlier in the course. And what we saw was when we had a negative discriminant, think about using the quadratic formula to find the zeros of that quadratic. A negative discriminant would indicate that this now only has imaginary roots. So it cannot be factored. Quite frankly, the only way it could be factored is if that discriminant turned out to be a perfect square. All right? The plain fact is, the fact that it's negative tells me I don't have any other real zeros whatsoever. And really, if you think about it, it kind of makes sense. When we go all the way back to the original graph, the only real zero that this function had was x equals 2. And therefore, we would not expect this quadratic to factor anymore, because if it did factor some more, we would get other zeros. I mean, forget about factoring. Even if it had a positive discriminant, we would at least get real zeros that were irrational possibly, but we don't get any more at all. And that is always the case with the difference of perfect cubes. You always end up getting this one linear factor and then what's called an irreducible or prime quadratic. I like both those names, irreducible, but prime's really nice. Prime means it can't be factored anymore, and that's what you get. Now let's just kind of really nail down what we have. What we can now say is that x cubed minus 8 is equal to x minus 2 times x squared plus 2x plus 4. All right? And it's been a little while since we saw them, but remember, this was that pattern that we had for the difference of perfect cubes. X cubed minus y cubed is x minus y times x squared plus xy plus y squared. And strangely enough, if you had this memorized, you could just write this right down, right? Because what you'd say is you'd say, oh, x cubed minus 8, that's x cubed minus 2 cubed, right? And then using this pattern, that would then be x minus 2 times x squared plus 2x plus 2 squared. And of course, that 2 squared is then the 4. Now again, for many students, the preferred method is just to memorize this. But the key is, if we can simply figure out a zero, then that allows us to figure out a factor. And if we can figure out a factor, we can then use polynomial long division to to come up with the quadratic. And you might say, well, that's a lot more work than memorizing all of this. Except you don't need to memorize anything with that. You already know the connection between zeros and factors, and you already know how to use polynomial long division. So use those tools that are at your disposal. Let's do a little bit more. All right, let's do a sum of perfect cubes. Exercise number 2 says, consider x cubed plus 27. Determine the only real zero of this expression, and then use this along with polynomial long division to completely factor the expression. Let's take this in stages. First, see if you can figure out the only real zero of x cubed plus 27, and as a little push in the right direction, you can find the zero, not surprisingly, by solving the equation where you set the expression equal to 0. So why don't you go ahead and try to do that? All right, well, it's pretty simple. We then say x cubed equals negative 27. We then take the cubed root of both sides, and unlike square roots, cubed roots have no problem with negatives underneath them. And the cubed root of negative 27 is negative 3. All right, so that is the only real zero. X equals negative 3. Now, because x equals negative 3 is a 0, what would have to be a factor? Well, it should be x plus 3, right? So this should be the only factor. Well, not the only factor, but it's got to be a factor of x cubed plus 27. Now let's figure out the quadratic factor. Okay, so just like before, what I want to do is I want to try to do this division. X cubed plus 0x squared plus 0x plus 27. All right, I'd like you to pause the video right now and see if you can work through this polynomial long division. Okay, let's go through it. Just like before, I'm going to have an x squared up here, and then when I do x squared times x plus 3, I'll get x cubed plus 3x squared. Again, I just want to do the subtraction, so what I'm going to do is I'm going to switch both of those to negative and do an addition. That's going to wipe those out. It's going to leave me with negative 3x squared. I'm going to bring down plus 0x. All right. That means I'm going to get negative 3x. Negative 3x times x is negative 3x squared. Negative 3x times positive 3 is negative 9x. Again, I need to subtract these, but instead what I'm going to do is change their sign and add. Those two are going to wipe out. 0x plus 9x is positive 9x. Drop the plus 27, and now I'm going to need plus 9, and that's going to be 9x plus 27. Now I'm going to subtract and get 0. You know you've done good things in these problems when you have a remainder of 0, because it tells you that that is in fact a factor. If that's not 0, and you know that's a factor, then that's going to be wrong. All right? But we've got it now. In fact, we can say as our final answer that the correct factoring is x plus 3 times x squared minus 3x plus 9. And just like before, the quadratic cannot be factored anymore. This can't be factored. If we did the discriminant on it like we did before, what we would find is that the discriminant would turn out to be negative, meaning that there are no other way to factor this, not using real numbers. See, I always get a little bit tongue-tied with things like that because, quite frankly, there's nothing that is unfactorable. If you start to include irrational numbers, if you include complex numbers, we can still factor this. But if we're only using rational numbers, there is no way to factor that expression. So that's it. We didn't have to memorize a fancy expression for the sum of perfect cubes if we could figure out the 0, the factor, and then new polynomial long division. Okay? Take a moment, write down anything from the screen that you need to, and then we'll do some more general work with sum and difference of perfect cubes. All right, let's do it. Now, what do I mean by more general work? Well, now I actually want to come up with those formulas that we saw with like x cubed minus y cubed and x cubed plus y cubed. Here I'm going to use a instead of y, but whatever, it's just a letter name. So exercise number 3 says, use polynomial long division to factor x cubed minus a cubed and find a general polynomial identity for the difference of perfect cubes. All right, maybe it should really say use polynomial long division to factor this in order to find a general polynomial identity. So that's what we're going to have right away. All right, now the key is, right, for x cubed minus a cubed to be equal to 0, x would have to be equal to a, right? Just think about it. If I put a up there, a cubed minus a cubed is most certainly 0. And of course, what that then tells me is that x minus a must be a factor. It's got to be. If x equals a is a 0, x minus a is a factor. So let's do that polynomial long division. Here we go. X minus a divided into x cubed plus 0x squared plus 0x minus a cubed, right? We want to divide this into that. Let's do it. So we're going to have x squared times x is x cubed minus a times x squared. Now the only difference between what we're doing here and what we really did effectively in exercise number 1, I think part C, is that there we had x minus 2, here we have x minus a. So a little bit more symbolic, a little more abstract, it can become more confusing. So just stick with me. I want to subtract this from this. Yet again, I'll change the signs and add. Those will wipe out. We'll get ax squared plus 0x after I bring that down. Again, I just want to match up. I want to subtract off the ax squared. So we're going to have plus ax. All right, ax times x is ax squared. Ax times negative a is negative a squared x. All right, again, that can be a little tricky. Ax times x, ax squared. Ax times negative a squared x. Think about it, a times a, and then the x comes along for the ride. Just like before, let's change the signs and add. Those cancel. We get a squared x minus a cubed, all right, which means I want to do an a squared there. A squared times x is going to give me a squared times x down here. And then a squared times negative a is negative a cubed. Change, add, remainder of 0. Remainder of 0, yay! But now we have it, right? Because now what we can say is that in general, x cubed minus a cubed will be x minus a times x squared plus ax plus a squared. And that's it. The difference of perfect cubes. X cubed minus a cubed is x minus a times x squared plus ax plus a squared. Yay! Let's take a look at the sum of perfect cubes. All right. Exercise 4. Show that x equals a as a factor of x cubed plus a cubed. Then use polynomial long division to find a general polynomial identity for the sum of perfect cubes. All right, first, let's talk about this first part. Show that x plus a is a factor of this. Well, we could actually use polynomial long division to do that. And the way that we could do it with polynomial long division is just see that 0 remainder at the end. But one way to really see that this is a factor of that is to say, well, x plus a is equal to 0, x would be equal to negative a. Now I can easily show that negative a is a 0 of that expression, right? Because if I had negative a cubed plus a cubed, that would be negative a cubed plus a cubed, which would be 0. All right? So since x equals negative a is a 0 of this expression, x plus a must be a factor. Now let's do the polynomial long division. So we're going to do x plus a and divide that into x cubed plus 0x squared plus 0x plus a cubed. Now what I'd like you to do is pause the video now and see if you can handle that polynomial long division. All right, let's go through it. Here we go. Just like before, we're going to start off with a little x squared up here. X squared times x is x cubed plus ax squared. Change the signs and add. Those cancel. We'll get negative ax squared plus 0x, all right, which is going to give us minus a times x, negative ax squared minus a squared x. Here's where it gets, again, a little tricky. Change the signs and add. Those cancel. Gives me a squared x plus a cubed once we drop that down. And finally, little plus a squared there. Gives me a squared x plus a cubed. And when I subtract those, we're left with a remainder of 0. All right. And again, put a little subtraction sign in there. Right now, we can write x cubed plus a cubed as the product of x plus a times x squared minus ax plus a squared. So x cubed plus a cubed is equal to x plus a times x squared minus ax plus a squared. And this is that general polynomial identity for the sum of perfect cubes. Your teacher may ask you, may require you to memorize this. That could be, right? You won't see the sum and the difference of perfect cubes coming up nearly as much as the difference of perfect squares, but it does arise here and there. Pause the video now for a little bit if you need to write any of this down, and then we'll wrap up the lesson. All right, let's do it. So today, we looked at two very special polynomial identities, the sum and the difference of perfect cubes. X cubed minus a cubed equals x minus a times x squared plus ax plus a squared. And x cubed plus a cubed is equal to x plus a times x squared minus ax plus x squared. Whew, that's a mouthful. And I definitely have them memorized, but I'll be honest with you, 2 months from now, maybe I'm in the middle of summer vacation. If somebody asked me, I would say, I'm not sure what x cubed minus 8 factors as, but I'd be able to figure it out because I'd be able to figure out that x equals 2 is a 0. I would then know x minus 2 is a factor, and then I could use polynomial long division to figure out the other factor. That's one of the best things about polynomial long division, is if you know one factor, you can figure out other factors by using that division. And sum and difference of perfect cubes is no different. All right. Well, I hope this video helped you a little bit with this challenging topic. Until next time, let me just say thank you for joining me, Kirk Weiler, for another Common Core Algebra 2 video by eMathInstruction. Until next time, keep thinking and keep solving problems.